right, kiddos. So, let me tell you what is so cool about what we're going to learn today. Let's say that you are Tom Hanks, and you have been stranded on an island, and you're trying to get off. And in order to get off of the island, you have to calculate the sine of point 1 to launch your boat at just the right angle to go over the wave.
What does being Tom Hanks mean? Why about to be Tom Hanks to be on the island?
Your ambition is to create the vision.
I'd much rather.
So skeptical. Okay, so you're there.
I'll just be in a jet plane flying on the island.
And you have to calculate the sine of point 1. Okay? How are you going to do it? You have no calculator. You were washed ashore. Barely anything. Okay. I will teach you today how you can survive the desert island now. Okay. Through mathematics. Through Taylor polynomials. Okay. So we are going to find polynomial, and let's pause for a second and make sure we all understand this algebra term, polynomial. Give me an example of a polynomial. 3 squared plus x plus 2. Okay. There's a polynomial. Another polynomial. Besides a square. Alright, there's a polynomial. Cameron, give me a really big degree polynomial. Well, that's really big. How about x to the 50th minus 9x to the 31st plus 2? Okay.
2,000 x to the 7th.
Yeah, okay, those are some polynomials. Is this guy a polynomial?
Yeah, yes.
No, okay, you can't have negative exponents. That is not a polynomial. Is this guy a polynomial?
No.
No, okay, that's trigonometric function. Okay, so we are going to find polynomial approximations of elementary functions. So meaning like sine x, maybe e to the x, okay? And what we're going to do is we're going to see how these polynomials are really, really close to the actual functions and be able to plug in values. Okay? So what will we be doing? Using polynomial functions that approximate another function. So let's just kind of start with a tangent line approximation. So a tangent line, okay, and it says here at x equals c. So if x is c, what's your y? F of c. Okay. So how would I find the tangent line? Okay, so we need to find f prime evaluated at c, and that gives me my slope at x equals c. Okay, and then what equation do I start with? Okay, y minus y1, which is f of c, equals the slope. And that's what we would use. Now I'm going to go ahead and just solve for y here. And we have this. That is our first degree polynomial approximation for any function. So a tangent line has a degree of 1. Why we call it the first degree. Another way, instead of saying y, is to say that I want p sub 1 of x. So my polynomial function of degree 1 is equal to this guy. Okay, so let's see that just in this first example. Again, it says find a first degree polynomial function p. So a first degree polynomial function p is also just known as the tangent line. And we've also got another word for that. Well, actually, it's two words. Another concept. Starts with an L. Yeah. Okay, so the local linearization. Okay, so now we just have another word for a tangent line. It is the first degree Taylor polynomial here. So it says find that whose value and slope agree with the value and slope of f at x equals c for this function when c is 8. Okay, so we had this function, and I'm going to go ahead and just rewrite it a little bit. That would be x to the negative 1/3. And we know we're going to have to find the what of this derivative. So let's go ahead and do that. Oops, I just put c's here, sorry. I don't know why I was doing that. Those are x's. My bad, guys. Okay, so that's f of x is just 4x to the negative 1/3, and f prime of x is negative 4/3 x to the negative 4/3. Everybody good? So then I'm now going to evaluate it when c is 8. So let's go find f of 8. That would be 4 over 8 to the 1/3, which would be 4 over 2, which is 2. F prime of 8, can you guys go do that? So I already said the cube root of 8 was 2. 2 to the 4th is 16. Okay. So now I can say that my first degree polynomial is y minus what?
2.
2 equals negative 112 times x minus 8. But we're going to write that in terms of p sub 1. So p sub 1 of x is going to equal what now? Add your 2 over. Good. Okay, so if I want, and I can do it, if you want to do it with me, you can. But let's say I go put this into, oops, that's not what I wanted. No, it's not on there. I put it into my calculator. Will you go hit TI in the little search guy right there so I can open it? Yeah, it will come right up once you just hit TI. Okay. I had it all open and ready before we shut it down. Alright. So in my y1, I'm just going to put the original function. So it was 4x to the negative 1/3, right? No, because I didn't use parentheses.
Oh.
So I don't know why I just erased that. 2 minus, do you want me to use it as a fraction? Make it more comfortable?
Yes, please.
Okay. But no, only if I had parentheses would it do that.
We're picky.
Okay. Good. You're welcome. Okay, so I'm going to zoom standard. And here is my graph of the original in blue. And then here is my graph of my tangent approximation, my linear approximation here. And where did we center this around? 8. So as I go and look here around the 8, what do I notice is happening? I do intercept right there at 8, but like as far as everything else, is that a pretty good approximation? Okay, so what we're basically saying here is, let's say that, I gotta remember what that graph looked, what, like this, was the other one above it? Okay, maybe, I don't know, something like that, okay? And we centered it here around 8. So what if I wanted to go over here at 9 and actually find f of 9? Well, do you know the cube root of 9? No. Well, we could try to approximate that, but we have this approximation right here that I could plug in. So I could plug 9 in to this guy, and I could get my answer pretty quick. What is that, actually? 2 minus 1/12, which would be, what did you say? 23/12. Okay? So we said here at 9, using the linear approximation, we can approximate that original function. Well, what's this distance between them? What's that called? Yeah, that's my error. Okay, so the distance between them is your error going on. It's how far off you are. But do you think we got a pretty good approximation? Sure. Okay, so what if I wanted to go out to 20? Do you think I'm going to get an approximation that is good? No. Okay, because it's not close to where I'm centered around. My error is going to be very, very large as I move away from where I am centered. What would be something that I could center it around? I think the cube root of 8, 27, I guess, would be a little closer, okay, that we could actually find the values of. All right, so, but that's going to be that error. Guess how I can make the graph of the polynomial become even a better approximation? We're not going to stop at just the first degree. See right here?
We're going to go to the 10th, aren't we?
There's what we just had, agreed? We just had that. You guys didn't even know this happened. You were at the cute little tangent lines just approximating when you have this huge Taylor polynomial that you could do, okay, to get an even better approximation. So you actually start with what you had for the tangent line, but you're going to go out in a bigger formula and a bigger pattern. So if you look at the pattern, this actually started the pattern, you just didn't quite see it. This was your x value minus your c to the 0, just like we didn't take any derivatives, and all of that goes to 1, so we don't see it, over 0 factorial, which again is 1, so we didn't see it. This was the first derivative, x minus c to the first over 1 factorial, so did I need to see it? No. Then I take the second derivative, x minus c to the second over 2 factorial. Then I take the third derivative, x minus c to the third power over 3 factorial. See how they match? And you keep going as far as you want for that degree. Okay? So you can actually get an even better approximation than just a linear. Joy. Okay. Now, when realize it's just x, 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 right? You don't have to have x minus 0. If you want to, just for the pattern, great. But this guy is called a Maclaurin. And a lot of times they're just going to say, hey, find the Maclaurin polynomial. And this is my little mnemonic device. And you guys can laugh if you want, but whatever. So I think I'm going to eat a Big Mac, you know, like a Maclaurin. And as I go to take a bite, what shape does my mouth make?
I know.
An O. Okay? So I am centered at 0. That's my mnemonic device. That's what I think of. Mac, 0. Okay? So however you want to think of it, but that's how I think of it. So
You had us do one of those on the test.
I did, but it was an easy thing to just do. It wasn't like you needed to know that. Okay? So, that's good that you remembered that though, Chris. When you hear Maclaurin, you think centered at 0.
Oh, poop.
Okay, so these are your steps that you're going to take. You're first going to go find your derivatives as far out as needed. Then you're going to plug in your C values here. Okay, so you're going to go plug in your C values into those derivatives. So then you'll have this, 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 and this once you find those. And then you're going to fill in the rest of the parts. Okay? Here, I have another one down there. Make it correspond better. So we're going to have this, 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 etc. And I'm also going to plug in my C's. So all of those things I plug in. They're like a plug-in chug. The X is kind of like a constant going on. That's always going to be in the formula. And the factorials will always be in the formula. Okay? So the things that change are what your C value may be and evaluating your original to your nth derivative at the C. Okay. So let's see if we can see it. Okay. So let's go out to the 4th degree. Close your eyes. Okay. We're going out to the 4th degree. First term is f of C plus f prime of C times x minus C. Okay, next term, plus f double prime of C times x minus C squared over 2 factorial plus f triple prime of C times x minus C to the 3rd over 3 factorial. One more. Next term. 4th derivative of C times x minus C to the 4th over 4 factorial. Okay, so kind of getting the pattern down. And so this is basically, as you get the more terms, you can get a better and a better approximation for something, a better fit. Okay? That's a power series. We'll get to those, okay? All right. Find the Maclaurin pause. 0. Okay, C is 0, centered around 0. Okay, I pause every time I see that word. C is 0. Okay. Find the Maclaurin polynomial of degree n for the polynomial f of x equals e to the negative x when n is 5. All right. First step. Get it all the way until how many derivatives? 5. Go. Sounds like it. Okay, if you don't want to keep using Roman numerals, then you can do like 2 or 3, 4, 5, but you have to use parentheses. All right? So if you don't use Roman numerals, get your parentheses. Okay, that's my first step. Second step, I'm then going to go and plug in where I'm centered. And evaluate all those derivatives where I'm centered. This one's just working out nice and pretty. Then I'm just going to fill in my pattern. You might start over on the left if you write big. Until you reduce things. Okay, so my pattern. First I do f of c, which is, try again, 1. Oh yeah, oh, okay. Plus f prime of c, which is -1 times x minus c, which is 0. Plus f double prime of c, which is 1 times x minus c squared over 2 factorial. Keep going in your pattern. You have to go to the 5th. And then see if you can clean it up. Let me know if you have questions. Yeah, and you can practice your factorials if you want. Knowing the 3 factorials, then it's 4 factorial. And while it's standard form, I know in polynomials to like go biggest to smallest. When we do particular polynomials, we're going to go smallest degree to biggest. Okay, so that's just how you're going to see it. And if you want to make a little note to yourself in your notes of where those guys came from, that's up to you. Kind of fun. Cool rainbow action. Okay. Is that okay? Okay, so now let's go look. Let's see how we did. So we first had e to the negative x. And then we had 1 minus x plus x squared over 2 factorial is 2 minus x cubed over 3 factorial is 6 plus 0. So I want to look close to 0. So there's my e to the x. Bum. It's taking a little bit of time. Oh, here it comes. Wow. That's where you guys are supposed to go. Ooh.
Yeah.
Okay, so look how good that approximates at 0. That's pretty cool. So again, if I wanted to go find an approximation over here at 8, is that a good idea? No, that error is going to be pretty bad. What if I wanted to approximate it at -9? Pretty bad. What if I wanted to approximate it at 2? Yeah. I would probably want to choose to go centered at around 1 if I could, but then I guess 1 I wouldn't know e to the 1 very well. But anyway, okay, so we got that. Yes? All right. I think for time purposes, we're not going to do this one. I think you kind of got it down. Okay, what those steps are. This is pretty basic. If you need more help, come see me. We can do that together. So now I'm going to talk to you about the error bound. So just like with the alternating series, you could find an error bound. We can with these Taylor polynomials as well. So if I went out and stopped at the nth polynomial, this guy left over is the remainder, right? And when I go and I take this actual, so whatever this guy was, this actual, minus the approximation of that polynomial, the remainder is error. Okay. So we have this error. And we have a formula for the error.
Ow!
Chris, leave him alone. Don't touch him. Okay, don't touch him. Okay, don't. Alright. So, we have a formula for this error. It is really similar to the alternating series. It is just the next term with a slight little hitch. Okay? So the slight little hitch, do you guys all see how this is the next term? It's the next derivative, the next power, the next factorial. What's the hitch? The z. Okay, and we're going to talk about that. Before we do, we're going to talk about what is the c value. C is where you are centered. Okay. What is this x value that I plug in? Because I'm trying to get a numerical answer for my error. The x is what I get for all of these guys. It's the value that I'm approximating at. Like, so if I am trying to find sine of 0.1, and I'm going to plug 0.1 into my polynomial, and that is my x value. Where am I going to center that? Probably around? Probably 0. Okay? So this is the value that you are approximating for. So then we have this guy right here. The absolute value of n plus 1 to the z is the max y value on the absolute value of f to the n plus 1 of x, so whatever that next derivative is, between x and c that we just talked about. And this is the tricky part. The rest isn't bad. So we're going to practice this, and then we'll come back to the full error bound. one more time to write the part. Let's look at this now. So we're going to practice this guy right here. Okay? So first we're going to look at f to the n plus 1 of x. So we're going to graph the absolute value of that. So we are actually graphing the absolute value of e to the x in this case, because that was my next derivative, the n plus 1. So let's look at the absolute value graph of e to the x. Does it change it at all? It's always above. So that's just our e to the x. Alright, and what two values are we looking between? We are centered at 0, and we are approximating x at 1. So those are the two values that I am between. So I'm going to look, what is the max output going on between 0 and 1? E. Okay? It occurs at 1, right? And we get out E. So f to the n plus 1 of z absolute value is E. And E may be hard to actually plug in without a calculator. So we could say, hey, E is less than or equal to what? What's an easy number we could plug in that's close to E? 3. Okay? And that's what I would actually use. We can always go a little bit above. It's going to make our error a little bit bigger, but that's okay. It shouldn't be that bad. Okay, let's look at this next one. So first graph the derivative of the n plus 1 of x with absolute value. We want the absolute value. And again, does that change my graph? But now I am looking between negative 0.1 and 0. So where is this max at? Okay. So the max here is at 1. It's the y output. It occurred at 0. So f to the n plus 1 of z, in this case, is just 1. And that's easy to use. Okay, try the next one with your buddies. Oh, because when we go plug it into the formula, again, I don't know what E is. If I knew what E is, you know, like, I could get out every value. Yeah, E is a rational number that goes on forever. That would take too long. So that's why we're just giving it an upper bound that's close to it. so what happens, whoops, what happens here? The negative e to the x actually gets flipped up. Okay, so I'm basically just back to e to the x. And we are looking between 0 and 1. And what is my max now again? It's going to occur at 1, which is e. And again, I don't know e very well, so unless I have a calculator, I'm just going to use 30.
It's gonna take 1/2.
Huh?
Oh no, that's the next one.
Okay. Okay, look at the next one with your buddies. Did you guys get that for the absolute value? Maybe it looks a little bit prettier than mine, but okay, we got the gist. All the negatives, like they would be down here, right? They get flipped up from where that would have been. Okay, so we are looking between what and what here? 1/2 and 1. Eee! That's before, right? So I really don't care. I just have like 1/2 and 1 somewhere. Okay. Oh. So where would this max be at?
1/2.
Okay, so it would be f to the n plus 1 of z, absolute value would be at sine of, or not sine, sorry, cosine of 1/2. But again, do I know what that is? So let's pick something a little bit easier. 1. Just make it easy. Like your upper bound here is 1. It's the biggest, like for any sine or cosine, and that's typically what we're always going to pick for sines and cosines, regardless of where we're centered in our x value is. Okay? Okay. Now, ready to go back? What did I do? You're good. So, cosine. Yeah. Oh, that's my 3. Okay, thank you. Oh, thank you. Okay, now I got you. I was like, that's not wrong. That was definitely wrong. Gracias. Okay. Good job. Austin. Okay, the third Maclaurin polynomial for sine is given by this guy. Okay, so it's just the third degree. Oh, hold on. The third Maclaurin. Okay. Centered at 0. Polynomial for sine is given by sorry. This is the same as the Lagrange. That's what we just saw. Right? The Lagrange or Taylor's theorem. You could call them both ways. It wants me to approximate the sign of 0.1 by p sub 3 of 0.1 and determine the accuracy. Okay. Well, let's go ahead. Sine of 0.1 then is going to be approximately what? P sub 3 of 0.1, which is equal to, who just left that door open? Zach? Hello? Okay, which is equal to what? Nope. Plugging it in. Yeah, 0.1 minus 0.1 cubed over 3 factorial, which is 6. Alright, we can do that. We can do that without a calculator. Let's see. 1/10 minus 1 over 1, 2, 3. 1 times 6 would be 6,000, which would equal, we need to multiply by 600.
599 over 6,000.
Okay, minus. Okay, so without a calculator, we could approximate what sine of 0.1 is. It didn't take us very long. And I'll tell you what that decimal is, just so you kind of can see, if you wanted to see what sine of 0.1 actually was. 0.09983. Okay, so that's what that decimal is approximately. Okay, so now let's determine the error. So we have the formula that says the absolute value of the actual, which is sine of 0.1, minus the approximation, which was 599 over 6,000. So the actual minus the approximation. And again, could I flip-flop those since they're in absolute values? Yeah, and sometimes AP will flip-flop them. Sometimes they'll write it. Okay, just for that context. Okay, is less than or equal to what? This is where we went out to the third, right? So we need to go to the fourth. Agreed? Because we stopped at the third. So we go to the next one. So I'm going to do f of the, so the what derivative? Fourth derivative of c times Rx 0.1 minus Rc 0 to the fourth over 4 factorial. Okay, so again, we're back to that tricky part that we practiced. What is the fourth of just x? Well, what was our original? What was f of x? Sine x. What's the first derivative?
Cosine x.
Cosine x. Keep going until you find the fourth derivative. Where are you back to? Sine x. between where? 0 and 0.1. So I know the max absolute value would be sine of 0.1, but WTF, right? That's what we're trying to approximate. I don't think we're going to use that. So we can say, hey, this guy is less than or equal to 1. Okay, 1 would be the complete upper bound that I would get out. Okay, so there's my sine of 0.1, but again, I don't want to try to figure that out by hand. That's what I'm trying to figure out by hand. Okay, so this guy we can plug in now to be 1 from right here. Okay. Okay, so I'm going to rewrite it. Sine of 0.1 minus 599 over 6,000 less than or equal to now 1 over 0.1 to the 4th over 4 factorial, which is equal to 1 over 10,000 times
24.
24, which is equal to 1 over 240,000. And in the problem, so that's our error is smaller than that, just by going to the 3rd degree. Isn't that pretty cool? That's a really tiny error.
Obscenely small.
Yeah, it was just the 3rd degree polynomial too. Okay, so they might, though, tell you, they might say, show that the error is smaller than 1 over 2,000. And have you done that? Yeah, so again, at the end, you would just have to tell me what? This guy is less than, yeah, okay? But I just made that up. But I'm just saying that they could have said that. See? Isn't that cool? You just found sine of 0.1 with an error of less than this number. That's so cool. You don't even think so.
Please don't use that quiz to me. It's giving me a headache.
Oh my goodness. Okay, we're going to come back to that. I want you guys to do this right here. Try to do this one on your own. Write out your whole pattern and then see what happens when you reduce. Don't try to do it in your head. Good job! How many of you guys got C? Tell you what you forgot. Factorials. So that's where you kind of first start, just the general formula, and then you got to reduce. So 6 over 2 factorial is 2, which would give me 3. 12 over 3 factorial is 6, which would give me 2. So the answer was E. Okay. And that's, actually, we can go fill in our potential questions so far. That's what we're going to pause today, because I want to go over your tests. So, 1, 2, and 3. So you can answer 1, 2, and 3. We're going to do number 4 tomorrow.